so today we're going to kind of like move forward away from the sequences and series stuff, although this kind of does fit in with sequences and series in the sense that it will generate a set of numbers that is a sequence. So recursive functions, the difference between like a recursive function and the stuff that we've been using before is that when we look at recursive functions, these are functions where we need to know either the term number or the previous term's value in order to generate future terms. So that's essentially the definition here. So these are functions that use the previous term or maybe previous terms to generate future terms. Okay, sometimes they also just use the n value in their equation. So that could be considered recursive as well. So a lot of times with recursive functions, if I'm trying to find like term 20, I need to know term 19 in order to do that in my equation. If it just depends on the n value, a lot of times like I can, of course, if I'm trying to find term 20, I can just plug in 20 for n. So sometimes you don't need that. But for most of our recursive functions, we need to know the exact previous term in order to get that next term. So that's kind of the difference between like your arithmetic sequence, geometric sequence, because with once we create a general equation for arithmetic sequence and geometric sequence, I can find any term in the list that I want. But for these recursive functions, usually what I need to know is the previous term before the term that I'm trying to find. So if I'm trying to find term 100, I need to know term 99, that kind of idea. Okay, so we have been introduced in our previous equations to Tn, which is the value of term n. So if we see T10, it's the value of term 10. What we haven't seen yet is this little guy right here. So if Tn is the value of term n, Tn minus 1 would be the value before term Tn, or before the value of term Tn. So for instance, if I'm looking at the value of term 10, Tn minus 1 is term 9. Okay, so if n is 10, then term Tn minus 1 is term 10 minus 1, which is 9. So it's just the term before the term Tn. Okay, so recursive functions, you need to usually know that term before. Explicit functions are the functions that we've been learning about all along. So for instance, our arithmetic sequence formula and our geometric sequence formula, these are called explicit functions. And I can find any term at any time as soon as I have those general equations. So these are functions like our arithmetic sequence or geometric sequence. Keep messing this up. Okay, so with our explicit functions, like our arithmetic sequence and geometric sequence, we can find like term 20 with only knowing like the first term and let's say the d value or the r value. So these can be really helpful, but the problem is that I can't express every single thing as a geometric sequence or an arithmetic sequence. Sometimes my sequences might have a pattern where they get multiplied by 2 and then add 3 to get the next term, right? And then it's both geometric and arithmetic, so how do I have a singular formula for that? That's when we need to use recursive functions. The Fibonacci sequence that we looked at a couple days ago, that's neither arithmetic nor geometric. We add the 2 previous terms to get the next term. So I actually have to use a recursive function to represent that sequence, right? So recursive functions we can do a lot more with because they can be any type of pattern. Whereas arithmetic and geometric, it can only be if I'm adding a number consistently or subtracting a number consistently or multiplying. Those are the only things that fit into those sequence formulas, right? So recursive allows us to do a lot more with a bunch of different patterns. Is everyone okay if I flip here? Yeah, okay. All right, so I'm going to show you a sample of how we use recursive functions. This is a little bit easier because it gives us the function, and then we just find future terms in it. And then we're going to go backwards and see if we're given a sequence, if we can find the pattern and create a recursive function from it. So in plain English, this formula right here is telling me to get the next term, take the term before it, which is Tn minus 1, and subtract 2. That's just in plain English, right? To get Tn, or the next term that I want, take the term before it and subtract 2 from it. Okay, so just to give you guys kind of an idea, if I'm trying to write the first 4 terms, I need to be started out with at least the first term so that I can get the next terms. If I don't know where I'm starting, I can't go forward from there. So if I'm trying to find the first 4 terms and I already know term 1, what would be my next logical term that I'm trying to find? Okay. So term 2 means I'm plugging in 2 for the n's here. So we'll have t2 minus 1, and then subtract 2 from that. And then I'm just going to actually simplify this little subscript here of t2 minus 1, which will give me 1 minus 2. And do we know the value of t1? 7. So I can actually replace t1 with its value from above with 7, and then I will get my next term. So term 2 equals 5. Okay, I have to do this kind of like sequentially, because I'm started with term 1, the only thing I can get from that is term 2, and then once I have term 2, then I can find term 3, and so on. Okay, with this formula, I couldn't find term 20 because I would need to know term 19 to find that. Okay? So just to give you an idea, I think we could probably continue this pattern ourselves, but just to give you an idea of how the formula works, now if I'm trying to find term 3, I'm going to replace these n's with 3. And then 3 minus 1 simplifies to term 2. So I'm actually going to use this term 2 that I just found in my first calculation, and I'm actually going to plug that into my formula. So replacing term 2 with its value, I get term 3 equal to 3. Okay? Now, if you can kind of understand what the formula is telling you, do you necessarily need to plug this all in to your formula? Probably not. You could show me maybe one substitution into your formula just to show that you know how it works, and then you can kind of go from there. So right now we have 7, 5, 3. What's the next value? 1. Yeah. So I don't really need to necessarily plug this into my formula if I know that I'm just subtracting 2 from every term. But one substitution at least would just be nice, just so that you can show your understanding of the formula. Questions for this one? Nicole?
So this is a recursive
This is a recursive function. So there's actually two ways that I can write this function. This is the recursive version, but if I know I'm simply subtracting 2, would this fall into arithmetic or geometric at all? It does, actually. So not all recursive functions will fall into that, but this is actually an arithmetic sequence. So the explicit formula for this is actually just the arithmetic formula with A and D plugged in. So I could also express this in its explicit format like this. Okay? The recursive format uses the previous term to get the next term. And again, I won't always be able to do this, right? If I have like a multiple and an addition or a subtraction, then I can't do the explicit formulas. Okay, so this is like our A and our D. Okay, let's try another one. So this one is a little bit different. Can somebody tell me what this formula is telling us to do in plain English? Katie?
To get the next term, take the term 4 and add 4.
Okay, so close. There's something that we need to do before we add 4. Okay, so to get the next term, which is tn, we need to take the term before it, multiply by 2, and then add 4. Okay, so that's the pattern of our sequence that we're going to develop. Times 2 plus 4. Derek?
Can you simplify?
What do you mean by simplify?
Like just make T1 plus 2.
T1 plus 2.
Because it's 2T, can we just simplify?
I'm not sure what you mean. What would you simplify this to?
Like just T and then plus 2.
Like this?
Yeah. Or
No.
plus the n minus 1.
Like this?
Yeah.
No, you can't. Because multiplying by 2 and adding 4 is not equal to plus 2, right? Okay, so I'll show you one substitution into the formula here. But again, we don't necessarily need to use the formula if we know in English what is happening here. Multiply by 2, add 4 to get the next term. But I'm started with term 1, so the first thing I'm going to calculate is term 2, which means that wherever I see an n in this formula, I'm plugging in 2. Remember that this is a subscript and not like a multiple or anything like that. And then if I simplify here, you'll see that we simplify to get term 1. And I know term 1 is equal to 5. So I can actually sub that into my formula. And then I get 10 plus 4, which gives me 14 for term 2. Okay, so if you want, you can for sure like continue to plug into your formula. You can do term 3 next, and then you can do term 4. But I think here we can kind of just figure this out ourselves. So we want to multiply by 2 first, and then we're going to add 4 to go to the next set of terms. So if I want to continue this sequence here, we're going to take 14, and we're going to multiply it by 2. What does that give us? 28. And then we're going to add 4, which gives us 32. Okay. And then to get our next term, we're going to multiply by 2. What does that give us? And then add 4? 68. Great. Good. So those are our first 4 terms. Joey?
So you don't even really have to do that work, right?
We don't really have to do it. I would like to see at least one of these substitutions in here so that you can show how the formula works.
Okay.
But once you have that, I'm fine if you just continue the pattern that you noticed there. Kaylin?
I don't understand why you eventually.
Well, I'm asked to, the question asks me to write the first 4 terms. So I already have the first term. If I don't have the first term, I can't find any more. So then I'm just going to term 2. And then after that, I would go to term 3 if I wanted to, and then term 4, and so on. But I need to do it like sequentially. If I have term 1, I have to use that to find term 2, and then term 2 I'll have to use to find term 3, and so on. Okay? Any other questions? Okay. All right, so there's another format of notation that I just want to show you. You might see them asked in function notation. Essentially, when you see this asked in function notation, f at n is going to be essentially the same thing as tn, and f at n minus 1 is essentially the same thing as t minus 1. So f at 1 is essentially telling you the value of the first term. Okay, so it's really the same, but it just might look slightly different. So I'll just show you guys kind of one substitution in here. But in plain English, we know how to generate future terms. Can somebody tell us in English what we're doing? How do I generate future terms of this sequence? Liam? Yep, so to generate the next term, we're going to take the term before, multiply it by 2, and subtract 7. Perfect. So I already know the first term is equal to 2. So if I'm trying to find the first 4 terms, the next thing that I'll go to is term number 2. So in our notation right now, it's going to look like f at 2. So the function's value at term number 2. So here's what we'll get. F at 2 minus 1 minus 7. And remember, this isn't multiplication. This is just saying the function's value when n is 2. So I'm going to simplify in here. And do we know f at 1? Yep, f at 1 is 2. We can see that up here. It's given to us. So we're actually just going to replace f at 1 with its value of 2. Oops. Do that in purple. And then we can simplify. So it'll be 4 minus 7 to give us negative 3. Okay, so that's essentially how it works. I'm going to show you one more substitution into this formula just because it's new. So if we have 2, then we'll go to 3. So f at 3 is going to equal 2 times f at 3 minus 1 minus 7. And then f at 3 minus 1 will simplify to f at 2. And then where do I go from here? This is equal to negative 3. We just found it over here. Perfect. So we're going to plug that in from our last calculation, and then I'll get negative 6 minus 7, giving me negative 11. Okay, so I think we get the idea here. My first 3 terms are 2, negative 3, negative 11, and yeah, Alex? Oh yeah, sorry. Thank you. Okay, and then if I want to continue this sequence here, by all means, you can go ahead and you can do a 4th substitution into the formula. But I think we get the idea. We multiply by 2 and subtract 7. So how do I get to the next term in this sequence here? So how did you get that, Bonnie? Yep, negative 3. Perfect. So we do negative 13 times 2, we'll get 26, and then we'll subtract 7, and Bonnie said she got negative 33. And we could continue that if we wanted to. Okay, any questions on this one? Okay, so the big thing is just don't get confused. This is function notation. If you really wanted to, you could change it all to tn's if you're more comfortable with that notation. You just have to know that like f at n is equal to tn with the little subscript. But if you get a question like this, you can go ahead and change everything into your t's if you'd rather do that. Okay? Can I flip? Okay. All right. So we've seen our tn minus 1. If tn minus 1 is the term before tn, what's tn minus 2? 2 terms before tn. Okay, so let's see how this, so this one actually gives us the first 2 terms of the sequence. So if I'm writing the first 7 terms, I would need to continue this by doing the 3rd term, right? I already have term 1 and I already have term 2. Then I'm going to do term 3. So let's see what happens when we substitute 3 for all the n's in our formula. Okay, so when I'm simplifying here, I get 3 minus 2 is 1, and 3 minus 1 is 2. And do I know the value of terms 1 and 2? Yeah, I do. Term 1 is 1, and term 2 is also 1. So term 3 is 2. Okay, let's try it for term number 4. Term 4 means I'm plugging in 4 for all the n's. It's the same variable, so same value gets plugged in for all of them. And this simplifies to term 2, and this simplifies to term 3. So term 4 is term 2, which we know to be 1, and term 3, oh, no comma there, sorry, and term 3, which we just found as 2. So that gives us 3. Okay, so I think we can just kind of continue the pattern here. Basically, this is telling me in plain English, to get the next term, what do I do? Add the previous 2 terms. Okay, so to get term 5, for instance, what are the 2 previous terms? 3 and 4, right? Or 3 and 2 are the numbers, yeah. So I'll take term 3 and term 4 and add them together, and I will get 5, right? That's essentially what the formula is telling me. To get the next term, take the 2 previous terms and add them together. Do we recognize this sequence as something that we've seen before? Fibonacci, yeah. So here's what we've got. Yeah, Kylie's?
Is that like a new formula for
So these are all new formulas, but yes, this is a new thing here. It doesn't have to be tn minus 1, right? It could be tn minus 5. So take the term, to get the next term, I'm taking 5 terms before it, and I'm doing something to it, right? Further questions? Okay, so this is just 2 terms before tn, right? Rather than 1 term before tn. Okay, so what are my, if I want the first 7 terms, I need to keep going. So what's the next term in the sequence? Yep, I add the previous 2, so I add 3 and 5 to get 8. And then the next term? 13. So add 5 and 8, and we get 13. Perfect. And of course, we know we can continue this if we want to. This is Fibonacci. Questions on that one? Okay. I also told you guys at the beginning that recursive functions may also determine or depend on n as well. So that might be an element to a recursive function. It just depends on like the term number that you're trying to calculate. I still need at least the first term to start out a recursive function. So always I have to give you at least the first term if I want you to find the next ones. Okay, so if I have the first term, I'll just show you how this formula works here. I'm going to go to the next term, term 2, and I'm plugging in the same thing for all of these n's, right? Every single one of these n's should get the same value as I'm calculating. So term 2 will be equal to term 1 plus 3 times the term number, which will be 2, of course, because that's what we're calculating. And then we know term 1 is 0.2. So we're doing 6.2 for term 2. Okay, and then if you change to term 3, all of the n's get 3 plugged in for them. So we'll do 3 minus 1 plus 3, and then this n will also be subbed in for 3. So all of those n's should be the same because they're the same variable. So term 3 equals term 2 plus 3 times the term number that we're calculating. So in this case, it will end up being 9. Okay, and then do I know the value of term 2? 6.2, we just calculated it. Okay, so I can't really calculate future values until I do it in a sequence, right? Like I have to do the first term, and then the second term, and then the third term. And in order to get the 5th term here, I would need to know the 4th term, right? So what do we get here, 15.2? Okay, if you want, you can do a further plug-in, but I think maybe we will do the last one plugged in. Let's just do it down here. So term 4 means I'm going to plug in 4 minus 1 here, plus 3 times 4. So all the n's get 4's in them. And then I'm adding 12 to term 3. Okay, so I'll do 15.2 plus 12, giving me 27.2. So here's my sequence here. And of course, we know we can continue that if we want to. Joey.
So for this one, you have to use like these equations. You have
Yeah.
to make it work, right? It's like, what's the pattern in that?
Yeah, so this one's just saying like I'm going to take the previous term and add 3 times the term number. So, I mean, if you get kind of the hang of it, like the next one's going to be term 4 plus 3 times 5.
Yeah.
So if you get the hang of it, you can for sure continue it. Again, I want to see at least this first substitution. But yeah, this one was a little bit more complex, so I just showed all the substitutions.
Yeah.
Questions for this one? We're good? Okay. Now, when we're going the other way, this can be a little bit more complex, right? Because I could really have any pattern at all that it's not just going to be arithmetic or just geometric. It could be a multiple and an addition. It could have something to do with the term number. I have to kind of figure it out. So a lot of this is a little bit more like problem solving based in the sense that there's no one thing that I can tell you to do to figure it out. You just have to see if you can figure out the pattern and then work from there. Okay, so we're going to try a couple of them. I encourage you to try and like kind of think them out ahead of time, and I'll give you maybe a few minutes along the way to figure these out. But main pattern here, does anybody notice the pattern for how future terms are generated? Joey? Multiply by -2. Okay, so this is a geometric sequence, but we're going to write it as a recursive function. Essay? That would only happen if we were dividing by -2. So in this case, it doesn't become -1/2. So in order to find the next term of the sequence, what do I do to the previous term? I multiply it by -2, that's right. So can somebody create my equation for me then? What would a recursive function look like here? So to get Tn, close, not times 2. Okay, so I do -2 times the previous term, which will be Tn minus 1. This is my recursive function. I can also express this guy as an explicit function. We know how to do that. We just sub in the a and the r in the geometric sequence formula. But this is the recursive version of that. Okay, and then usually what I would give you is I would have to give you the value of term number 1, but we can already see that in our sequence here. Okay? Questions so far? Okay. All right, so this one is showing you in a graph the function's value versus the function's number. So you'll notice here, these ones all have to be whole values because it's talking about like term 1, term 2, term 3, term 4. So what is the value of term 1? 2, yep, you're right. That's right here, right, 2. What's the value of term 2? 6, yep. 3, 10, and 4? 14, very good. Okay, so we can see this here. So here's our sequence. It goes 2, 6, 10, 14, and so on. Okay, do we notice a pattern here? What's the pattern? Okay, so this is arithmetic. I should also be able to express this as a recursive function. So could somebody create our recursive function for us if we're adding 4 to get the next term? Alex?
Tn equals Tn minus 1 equals 4.
Yeah, that's awesome. Okay, so to get the next term, take the term before it and add 4 to it. That's it. Okay, I also want you guys just to see here that this actually creates a line. So when I'm doing arithmetic, it's actually, because I'm consistently adding 4, it's actually like creating the points of like a linear equation. So this is actually very similar to like y equals mx plus b, right? I could say like y equals x plus 4. That's the equation of the line that's formed by these points. So arithmetic is actually a linear, what we call a linear relation. The points form a consistent line. Questions for this one? We're okay? Okay. All right, we're going to step it up a little bit here and see what we can figure out. So I want you guys to take a couple seconds here, and I just want you to see if you can find the general pattern of the sequence. Let's just start with that, okay? I'm going to pause this for a second, and we'll take a couple seconds and see what we can figure out from this.
For just C or both?
Okay, so now that we've taken some time to find the pattern here, can somebody told me before, but somebody tell me the pattern that's happening here? Joey?
So like the first, from 3 to 5 is 2, and then from 5 to 8 is 3.
Okay.
It keeps going up by 1.
Okay.
I don't know explain that.
All right, so every time we're adding one more than the previous time. Any thoughts as to how we could create a recursive function from this? That's the challenging part, right? Liam?
So what I did was Tn equals Tn minus 1 plus in brackets 1 plus n.
Okay, so 1 plus n, do we need 1 plus n? Or Derek said he just used n. Kaylin?
Add them like in the previous question.
So the problem is that the value of the addition keeps changing though. So we need something to represent that value that keeps changing. So if I'm finding term 2, I'm actually adding 2 to get from term 1 to term 2. And then when I'm finding term 3, I'm actually adding 3 to get from term 2 to term 3. So Derek is right. It's actually, we're just adding the term number. Okay? You can do a check, and I would encourage you to check as you do this, just to make sure that your formula actually does work. So we would check, knowing that term 1 equals 3, we would check our formula for term 2. So for term 2, I'm taking term 1 and I'm adding the value of n, which is 2. Does that work? 3 plus 2 equals 5. So that gives me term 2, right? And then if I check it for term 3, my formula is saying take term 2 and add the term value that I'm trying to find, or term number. And 5 plus 3 equals 8. So I think we're good. Okay, so always look out for how maybe your addition is connected to that term value, and also the term number as well. Good job. Okay, did anybody get a chance to find our pattern for part D? No? Times by negative 5? Well, here we're adding negative 5, right? Okay. Well, if you're watching the video right now, take a second and pause this and see if you can find the general pattern. Alex, did you find a pattern here?
Goes up 3 times more than the previous sequence, 'cause it goes up -5 to
Interesting. So we know that this must have something to do with maybe multiple, some kind of multiple of 3. So if I notice here that these are being multiplied by 3, that's actually a pretty good observation, because that might actually come up somewhere in my calculation. So we need to kind of hash this out and see if we can kind of figure out how we can relate that multiple of 3 to our equation. Did you figure it out, Derek? Okay.
3Tn minus 1 plus
Okay, so Tn equals 3 times Tn minus 1, and then you add 1 to it? Okay. So there's that multiple of 3, and then we just need to figure out maybe an addition or something that works to kind of get us to the number that we want. So if you do a little check here, if we check this with terms maybe 2 and 3, T2 is going to equal 3 times 2 minus 1 plus 1, which is term 1 plus 1. That works for the first one. It's good if we figure out if it also works for the next ones as well. So sometimes something will work for the first one, but it won't work for the other ones. So we just need to double check. So let's see, 3 times term 2 plus 1, does that give us 23? Or negative 23, yeah. So that one works. And then if we just kind of follow the pattern, 3 times 23 is going to give us negative 69, and then plus 1 will give us negative 68. So this works. Good job. Okay, so a lot of this stuff, I know that this isn't like, there's not one standard thing that I can tell you. I would say find the general pattern and then see maybe if there's a multiple happening or how it's related to the term number or the term value, and then you kind of go from there. So these can be, they require a little bit of practice because there's no one standard way. Joey, can you take out your headphones? There's no one standard way that you can do every single question, right? Questions on this one? Okay. So adding even and odd values, sometimes you might see this in your worksheet or in your other work. Sometimes you will see that a sequence is adding, maybe it adds 1 and adds 3 and then adds 5 and 7 and 9. Or if it adds even values, maybe it adds 2, 4, 6, 8, and so on. So this one is adding 1 more than the term before it. But sometimes it goes up by even numbers or it goes up by odd numbers. So I can create even numbers by multiplying my term number by 2. Do we all agree that all even numbers are divisible by 2? So an even number, I could represent this with like 2n, or it could even be like 2n plus 2, or like 2n minus 2. It could also be like 2n plus 4, 2n minus 4, stuff like that. So things that keep it even. So if I take an even number and I add 2 to it, that's another even number, right? So if you notice that your pattern is consistently adding even numbers, it might be kind of something like this where we create an even number with the term value. If it's odd, if an even number is 2n, what's an odd number? So an odd number is either 1 more or 1 less than an even number, right? So if an even number is 2n, how do I create an odd number? So the simplest one is just 1 more than an even number. I could also do 1 less than an even number, but like Derek said, I can also do like plus 3 or minus 3, or I can do like plus 5, minus 5, that kind of an idea. So you can kind of use that idea to, if you notice that your pattern is going up by evens or odds. But a lot of this is just like a guess and check and see if it works type thing. Okay? So we're going to work on, for the rest of class, a little worksheet. I would encourage you guys, try not to look at the answers, especially for number 2, where you're trying to figure out the pattern. Try not to look at the answers. See if you can figure it out. Another little hint that I will give you is sometimes it adds like squares or cubes of the term number. So look out for like, maybe if you notice you're adding 4 and then 9 and then 16, those are perfect squares. So maybe you're doing like n squared or n cubed. So look out for like cubes and squares and stuff like that. Because you might see that it adds like some kind of exponent of the term number as well. Okay? Okay. All right, that's it.